This is chapter 12. Section 7 is addition reactions for alkenes. In an addition reaction, some sort of reactant is added to the double bond of an alkene or the triple bond of an alkyne, like you see here. In both cases, the atoms of the other reactant are incorporated into the structure of the carbon chain, and so no atoms are lost or replaced in the formation of this product. This is why it's an addition reaction. This is actually an example of a combination type reaction. In this section, we're going to learn to draw condensed structural and line angle formulas for the products of these kinds of reactions. There are several different types of addition reactions that all have a very similar mechanism, so we can learn them relatively easily all together. These types of reactions are hydrogenation, halogenation, hydration, and hydrohalogenation. Now these names are all a little bit similar sounding, and so it helps to think about what they mean. Hydrogenation is the addition of hydrogen, H2. Halogenation is the addition of a halogen molecule, usually either Cl2, chlorine, or Br2, bromine. Hydration is just what it sounds like. It's the addition of water. In this case, we tend to designate it HOH, which will make sense when we look at the mechanism a little bit later on, but it's just a water molecule. And then the last one is hydrohalogenation, where you're adding both a hydrogen and a halogen at the same time. In other words, you're adding something like a molecule of HCl, hydrochloric acid. In hydrogenation, an alkene or alkyne reacts with a hydrogen molecule to form a saturated alkane. You can see the mechanism depicted here. A hydrogen molecule approaches an alkene with the hydrogen-hydrogen bond parallel to the double bond in the alkene. This places one hydrogen over one of the carbons in the double bond and the other hydrogen over the other. These hydrogen-carbon pairs start to form new bonds between them as the electrons migrate from the hydrogen-hydrogen bond and from the double bond in the alkene. Eventually, the bond between the hydrogen atoms is totally broken, leaving them separate, and new bonds have formed between each hydrogen and one of the carbons that was in the double bond. So 2 electrons from the bond in hydrogen have gone to form one of these bonds, and 2 electrons from the double bond have gone to form the other. In this case, what we're left with is a simple alkane. It's written here with these hydrogens drawn explicitly outwards to show that they came from the hydrogen molecule, but we could also just rewrite this product as CH3 bonded to CH3. In other words, it's a molecule of ethane that's been produced by hydrogenating ethene. Let's take a look at an example of this. This question says to write an equation for the hydrogenation of 1-butene using a platinum catalyst. Let's talk about the hydrogenation of 1-butene first, and I'll come back to the platinum catalyst at the end. So here we first need to begin by drawing the structure of 1-butene, obviously. Remember that but is the prefix for 4 carbons. The ene ending means there's a double bond, and the 1 means that that double bond begins on the first carbon. So we can draw our 1-butene molecule like so. We start with 1 carbon. It's going to be double bonded to the next carbon, and then the rest of these are single bonds. I left some space for the hydrogens that we need to put in. For the first carbon, it has a double bond going to it, but it still needs 2 more hydrogens to make 4 bonds. The second carbon has 3 bonds already, so it only needs 1 hydrogen. The third carbon has 2 bonds, so it needs 2 hydrogens, and the last one needs a typical 3 hydrogens. So this is a molecule of 1-butene. This is going to combine with hydrogen gas. That's what hydrogenation is. It's adding hydrogen gas. And it's going to produce something. Well, what does it produce? Remember, the hydrogen molecule is going to approach parallel to where the double bond was. And that is where the hydrogen-carbon atoms are going to form. So what we're going to end up with is a molecule that has all of the same carbons with all of the same hydrogens, but none of the double bonds. So this double bond at the beginning is now going to be replaced with just a single bond, and all of the other single bonds will be the same. Then we also have to add in the 2 new hydrogens that we put from the hydrogen molecule. One is going to be here, and one is going to be here. In other words, they're going to attach to the two carbons that used to be in the double bond. So this is the overall reaction, the hydrogenation of 1-butene. It turns into butane. Again, we could take this structure and reduce this down so that we have 3 hydrogens here and 2 hydrogens here. And that might make it a little bit more clear that it's just a simple alkane, butane. As far as the platinum catalyst, the only thing you really need to know about that is that this reaction does sometimes require a catalyst to run, but you just write the catalyst over the reaction arrow. In this case, platinum is PT. So some of these addition reactions require one catalyst or another, either platinum or nickel or some sort of acid. Whatever catalyst you're asked to include, if you need to put it in, you just put it over the reaction arrow. You could also do this, by the way, using the line angle structures. So if we do that, then we could draw butene this way. 1, 2, 3, 4. The double bond is on the first carbon, so here. So this is 1-butene. Notice that there's no cis or trans because on this carbon you have 2 hydrogens coming off. So they're the same atom, and there's no cis-trans isomers for that. So we're not concerned with that right now. You combine this with hydrogen gas, and what you end up with is the same structure, but now you just don't draw in the double bonds. So hydrogenation is an extremely easy addition reaction to show the product of, because you essentially just copy the same structure you started from, but without the double bonds. And then, of course, the last thing you would need to do would be to put platinum over the reaction arrow to show that it's the catalyst. One place you might have heard of hydrogenation before is a place where you might also have heard of the terms saturated or unsaturated, the way that we have been using them. Vegetable oils are an example of unsaturated fats composed of fatty acids with double bonds. They're unsaturated because they have double bonds. Adding hydrogen to the double bonds in vegetable oils can increase their melting point by converting them into saturated fats. These make them solid at room temperature, so this is for things such as margarine or shortening. We'll learn more about this in the chapter on fats and oils. For now, let's take a look at a couple of other examples of hydrogenation reactions. Again, for each of these, you're just adding hydrogen to the double bond, and so it's very simple to draw the product. You can take a look at the mechanism this way and make sure that you're putting it in the right place, but really all you need to do is draw the same structure, but without the double bond, and making sure that you add in the correct number of hydrogens. Here, these 2 central carbons had 1 hydrogen to begin with, but after they each get a new one, they're each going to be CH2. So I need to add 2s down there. And then you're done. So this is 2-butene. We're not concerned about whether this is cis or trans because they haven't drawn the configuration out in a way that we can tell. But it doesn't matter because both configurations will hydrogenate into butane. For the second example, it's even easier. They give us a line angle formula, so we can just copy the line angle formula, but leave out the double bond. So in other words, a molecule of cyclopentene will hydrogenate into a molecule of cyclopentane. The next addition reaction we're going to learn about is halogenation. And this is virtually identical to hydrogenation, except now we're adding a molecule of usually either chlorine or bromine to the alkene. That means that instead of just getting a regular alkane at the end, we're going to end up with a haloalkane, an alkane that has halogen substituents. But other than that, the mechanism is exactly the same. The molecule of whatever halogen we're adding approaches parallel to the double bond in the alkene. In this example, we're going to look at chlorination, just to make it concrete. As the chlorine molecule approaches, a new bond forms between each of the carbons in the double bond and each of the separate chlorines in the chlorine molecule. The chlorine-chlorine bond breaks and the double bond shifts over to form one of the new bonds to the chlorine, and so we end up with an alkane that has chlorine atoms attached to the 2 carbons that were part of the double bond. From that, we should be able to predict and draw the products of reactions like this. The first example, we have propene plus bromine. The bromine molecule, again, is going to approach parallel to the double bond in the propene, and that's where the new carbon-bromine bonds are going to occur. You're going to break the bond between the bromines, and you'll also break one of the bonds in the double bond between those two carbons. So what you end up with is the same essential structure, CH2 bonded to CH, bonded to CH3. We now have a single bond instead of a double bond, and we're not adding any hydrogens in this time, so the hydrogens stay the same. But we are adding a bromine at this carbon and another bromine at this carbon. That's because those are the two carbons that were part of the double bond originally. So the name of this would be 1,2-dibromopropane. So we've still converted an alkene into an alkane, it's just now it has halogen substituents as well. For B, again, it's relatively simple, especially when you're looking at a line angle formula. For something like this, I would still just redraw the given structure, but without the double bond. But I still want to keep track of where the double bond was, because those are the two carbons that are going to get the chlorine atoms that we're adding. So this carbon will have a chlorine added to it, and this carbon will have a chlorine added to it. That would make this 1,2-dichlorocyclohexane. The next addition reaction is hydration. And hydration is where it gets a little bit different. We can still look at adding a water molecule, which is what hydration is, in a similar mechanism to the way that we added a hydrogen or a halogen molecule. So in other words, we can look at the water molecule, which is hydrogen attached to oxygen attached to hydrogen, and we can sort of compress down one of the hydrogens to go along with the oxygen, so that we're looking at just one of the hydrogen-oxygen bonds. The water molecule is going to approach the double bond in the alkene with that bond parallel to it. And then the same thing is going to happen as it happened before. That bond is going to start to break as those electrons migrate down to form a new bond between one hydrogen and one carbon, and one oxygen and one carbon. So at the end, we're going to end up with an alkane, again, where there's no double bonds, only single bonds, because we've broken the double bond. But now we have an OH group attached to one of the carbons. The problem with the hydration reaction is that the water molecule, when we envision it like this, isn't quite symmetric. It's not symmetric the same way that halogens and hydrogen molecules are. So if the molecule of water comes down in this configuration, or this orientation, I should say, instead, then it looks like we would end up with the OH group on the other carbon. So what's the answer? Which of these actually happens? Do they both happen? Do they both happen at the same rate? Well, it turns out if you look at the way this mechanism occurs and the stability of the intermediates, that this one on top is the preferred outcome. This is called the Markovnikov product. It's a consequence of Markovnikov's rule. That's the Russian scientist who first discovered this phenomenon. Again, the reasons for this are in the details of the mechanism, and they're a little bit beyond the scope of this course, but the rule itself was relatively easy to remember. In fact, the way that it's most often remembered is the rich get richer. In other words, the carbon that has the most hydrogens attached to it already is going to get another hydrogen attached to it in this addition reaction. The other carbon, which has fewer hydrogens, is going to end up with just an oxygen attached to it. And so it's going to stay with fewer hydrogens. This is the essence of Markovnikov's rule. In reality, both products are actually produced, but the Markovnikov product is the major product. So the distribution of products will be something like 80% of the Markovnikov product and only 20% of the lesser one. The different percentages will be different depending on the actual reaction and the chemicals and conditions involved. But in general, the Markovnikov product will be the dominant one, and that's the one that we're looking for when we ask for the product. So here's an example of this kind of question. It says, predict the product of the addition of HOH, or water, to the following alkene. We see here that the double bond is on this last carbon, and so we can imagine that the water molecule is either coming down like this, with the OH over this middle carbon, this internal carbon, or it's approaching like this, with the OH coming at the end carbon. The question is, which of these gives us the major product? Which of these gives us the Markovnikov product? And so remember the rules, the rich get richer. So the carbon that's richest in hydrogen, that has the most hydrogen, this one, is going to end up with more hydrogen here. So this top orientation is the correct one. This hydrogen attaches to this carbon, this oxygen attaches to this carbon, this bond breaks, the double bond becomes a single bond, we can forget about this orientation, and we end up with the following product. CH3, CH2, that's all the same, CH stays the same. This CH2 now has another hydrogen, so I'm just going to call it CH3 instead of drawing the hydrogen out explicitly. And then I have to remember to put this OH group on this carbon here. This is actually an alcohol because it contains an OH group. We haven't learned about the naming convention for that yet, but this is 2-butanol. The last addition reaction that we need to learn about is called hydrohalogenation. This is where you take a hydrogen halide, in other words, a hydrogen attached to a halogen atom like bromine or chlorine usually, and you add that to an alkene or an alkyne. The mechanism for this is pretty much the same as for hydration, and it still goes by the Markovnikov product rule. So in other words, the hydrogen halide can approach in two different orientations relative to the double bond. Just as with hydration, the hydrogen member of the hydrogen halide is going to go to the carbon that already has the most hydrogens attached to it, and the halogen is going to go to the other carbon. So just like with hydration, we can do an example of this. It says predict the product of the addition of HCl to the following alkene. So we find the double bond and we think about the two different ways that the HCl could approach. It could approach this way or it could approach in the other direction. If it approaches in this bottom direction, then this carbon, which is a part of the double bond, would get the hydrogen, but that carbon doesn't have any hydrogens. Instead, this carbon, which already has two hydrogens, is going to want to get the hydrogen. So it's this top configuration that actually makes the most sense and will lead to the Markovnikov product. So this initial carbon, the first carbon, is going to connect to that hydrogen, and the second carbon is going to connect to the chlorine. This bond is going to break, and you're going to end up with the following structure. You have CH2, but the CH2 becomes CH3 when you add in the new hydrogen. So it's CH3 single bonded to a carbon that is attached to a chlorine above and a methyl group below. That doesn't change. And then single bonded to a remaining CH3. So this is the end result of this hydrohalogenation reaction. Notice that everything else about the molecule stayed the same. So even though there was this methyl substituent down here, that goes along and that stays there by the end. Nothing happens to that. The only thing that happens is you add a hydrogen to this carbon and a chlorine to this carbon.